Scatterplots and lines of best fits. We're going to talk about the types of scatterplots, how to determine the strength of scatterplots, and using lines of best fit to predict some values. So first here we have three scatterplots. This first one actually shows a positive correlation. And when you say correlation, you can also say trend. Basically, these coordinates are all trending upwards as they go to the right. So as the x value increases, because we always read from the x, the y value also increases. That's what makes this a positive trend. On the middle graph, there is a negative correlation. This is also trend. Those words are interchangeable. And this is because these are going downward in the graph. So again, as the x values increase, because we always read x's from left to right, so as I move from left to right on my graph, my y values are actually decreasing, which is what makes it be a negative slope. And then on the final one, this is a no correlation or no trend. Basically, there is no pattern to these x and the y values. They're kind of just scattered everywhere. So they're not going up, they're not going down, they're just kind of randomly placed. Now, the strength of these trends is determined by what we call an R value. So we calculate the strength of a linear correlation of a scatter plot by basically seeing how close to a perfect line the data can get. So what we call this value is we call this the coefficient of correlation. You can also hear it as correlation, coefficient, any of those words that mean coefficient of correlation. And we represent this with an R. That's the variable we use. Now, this number, it's a number that's between -1 and 1. It doesn't go outside of those boundaries. So you will never have an R value of -2 or of +5. It has to be between -1 and 1. So I have a number line down here below. And so we have three trends that we like to look at. At -1, we call this a perfect negative. And that's because if I tried to draw a line of best fit, these are perfectly in a line that is going negative. At 1, on the other end of the spectrum, we have a perfect positive. That's because, again, these points are all perfectly in a line. That is the goal. We want it to be in a perfect line. But because the world is not perfect, we usually have ones that are not exactly -1 and are not exactly 1. Now, if you have an R value, a correlation coefficient of 0, that means this is no trend. That means your line of best fit's a straight horizontal line. So on the negative side, if we have R values that are closer and closer to this perfect -1, we call these strong negative correlations. So if we look at our picture here, this is still going down and all of those dots are still pretty close to that line. These are all pretty tightly knit on that line of best fit. So they're getting really close to being a line. Then we have like this middle ground of -0.5. And then on the right of -0.5, closer to 0, but still on the negative side, we call this a weak negative correlation. And again, if we drew that line of best fit, you can see that on this one, the dots are further spread out off of that line of best fit. So they're not quite as tightly knit together. So closer knitting to the line of best fit is a stronger correlation. Further apart, more spread out is a weak correlation. And since these are both trending downward, that's why they're both negative. Now on the other side, we have the same kind of idea. If we want numbers closer to 1, that perfect linear function, this will be a strong positive correlation. And again, if I draw the line of best fit for my example here, we can see that, again, the points are trending upwards, which makes it positive, and they're all pretty close to that line of best fit. They're pretty tightly knit together, which is what makes it strong. Positive is the direction, strong is how close we are to that line of best fit. And then, again, you have like a middle ground of 0.5, which is hard to tell whether it's strong or weak. And then we have closer to 0. So closer to 0, again, is a weak, but this time it's positive because the points are all trending upward. But yes, they're trending up, but they're pretty spread out from that line of best fit, which is what makes it weak. So strong or weak tells you how closely knit the coordinates are. How close to a line are they? Are they really grouped together? Or are they really spread out? And then the positive or the negative is the direction the coordinates are going. So we're going to use these R values and we're going to try to determine, is it a strong, is it weak, is it positive, or is it negative correlation? So I'm going to do 1, 2, 3, you do 5, 6, and 4. So number 1, R equals 0.2. Well, the number itself is positive, so I know that it's going to be a positive correlation. And the 0.2 is really close to 0, so I'm going to say that this is a weak positive correlation. I'm just going to say trend. For number 2, negative 0.1. Well, the number is negative, so that means it has to be a negative trend. And 0.1 is still close to 0 on the negative side, so this is weak. 0.1 would be about here somewhere. 0.8. So again, the number is positive, so it's going to be a positive trend. And 0.8 is fairly close to a 1. It's very close to that perfect line. So this is actually a strong positive trend. Pause the video, try 5, 6, and 4. And here's what you should have had for your answer. So pause the video, see if you can determine a reasonable R value, and then write if it's strong, weak, positive, negative, or no correlation based on the graphs. So here's what you maybe should have had. The R values can vary just a little bit. So if I drew my line of best fit for number 1 and I saw that the points were really spread out, but they are trending downward, so I said weak, negative. So for this R value, you could have had negative 0.1, negative 0.2, 0.3, anything that's really close to 0, not past that midway of negative 0.5 though. For number 2, this was the crazy no trend. And so with no trend, your R value has to be a 0. That's the only way to get a no correlation, a no trend. And then for number 3, these are going up, but they are very spread out off of that line of best fit. So it would be a weak positive. And again, this could vary. You could have 0.2, 0.3, 0.25, 0.24, anything like that. And then for number 4, this is a negative for sure. And these are very, very close knit to that line of best fit. They're very tightly grouped together. So that would be a strong negative. And so again, this could vary. You may have 0.8, 0.9, 0.85, 0.75, as long as it's on the right side of that midway point of 0.5. The next thing we need to talk about is what's called causation versus association. So with scatterplots, we have two ways to describe the data. We can either describe it as causation, and that is when one situation causes the other to happen, like cause and effect. Okay, so here's the example. So as the number of knots tied in a rope increases, the length of the rope decreases. So because you are tying more and more knots, that is making the length of the rope decrease. So this here is causing the length to decrease, therefore it's causation. Now, association is basically when these don't really cause each other. They may or may not. They don't have to. So here's a pretty good example. As the sales of Christmas trees increase at StoreMart, employee sick day usage increases. So you may be able to read into this and say, well, Christmas trees are in the winter, and winter is usually people get the flu. Yes, but that's not what it says. It's saying that because you're selling more trees, more people are getting sick, which may not necessarily be causing one or the other. So this would be an association. Just because this happened isn't mean that is why this is happening. So determine if the below is causation or association, and then determine if they have positive or negative. So pause the video, try the bottom two examples. And here's what you should have had. As the number of ice cream cones increases, the student absences increase. Well, just because you're selling more ice cream doesn't mean the school absences are going to go up. So that'd be association. Now, there is a positive trend. So just because one is not causing the other, you can still have a trend. So increase and increase, those are both upward directions. So that would be a positive trend. As temperature outside decreases, the number of people wearing coats increases. Well, this would be causation. When the temperature goes down, you're going to wear more coats. So this is causation because the temperature is causing this to increase. And it's a negative correlation because one is decreasing and the other is increasing. Let's talk line of best fit. So for example 1 and 2, we're going to draw in our line of best fit and try to find an equation for it the best we can. So I would like to draw a line of best fit. So what that means is try to get the same amount of coordinates above and below your line. Kind of get in the middle of all of your data points. So I can see that the y-intercept is here 2.5, 3, and so it has to be either A or B. Those are the only equations with a y-intercept of about where I need. So C and D are not correct. And now the next thing I can look at is I can see that this is a negative trend, which means it has to have a negative slope. So my slope has to be smaller than 0. And so the only letter that has a negative slope is choice B. Pause the video, try number 2. So for number 2, you should have had choice C. And so the y-intercept is pretty close to 0. Unfortunately, that doesn't help me because all of these have a y-intercept of 0. I know that it is a positive trend, so that means the slope must be positive. So that gets rid of choices B and choice D. Now, for choice A 4 slope is a very steep slope because think about how you graph. You would have to go up 4 and right 1. So it'd be something like this. If you graphed choice C, you'd have to go up 1 and right 4, so it'd be more along the lines of this. So the closest line of best fit would actually be choice C. Example 3 and 4 are predicting. So example 3, the graph shows what a household spent in tens of dollars on natural gas each day over the last 2 months. If the pattern continues, about how much will the household spend on natural gas on day 70? So we have some choices. So let's see if we can figure this out. How much will the household spend on natural gas on day 70? That means I'm telling you that the x is going to be a 70. And so x is 70 is all along this line. Now, you're trying to find the coordinate that fits the pattern the best if the pattern continues. So choice A means you're going to spend $50, which is here. That's way too high. That's not in my pattern. So it's probably not A. Letter B is saying 35, so 35 is about here. Well, that could be it because I see this guy's kind of weird too, so let's hold on B. Letter C is $5. Well, that would be here, and that's way too low. That's definitely not going to be it. And then letter D is 25. Well, if I were to look, because that's pretty close too, if I were to look at this pattern, D is a much better fit than B. So D is probably what they're going to spend on natural gas. So for number 4, similar idea. The scatter plot shows the number of hours that students studied and their resulting test scores. Answer the questions below. So letter A, if the students studied for 8.5 hours, what could they expect to score? So studying for 8.5 hours is giving me the X. So at 8.5 hours, that's about here. Well, what could you expect to score? You don't want to pick a point like here, not a 30. They could, but that's not in the pattern. You also don't want to pick something way up here either because that's too high. And so we want to pick a number that's pretty much right in the center of all my data. So maybe they would score about an 85. That could be a pretty reasonable guess. Now for letter B, if a student scored a 75, how many hours did they probably study? So if you're scoring a 75, that's your Y. So scoring a 75 is right about here. And so again, you don't want to pick something way outside the data point. So like here is probably not correct. Okay, they may have studied only for an hour and scored a 75, but according to the data, where could you expect it? Is you could expect it to be somewhere over here, maybe about 7.5 hours. And again, these are estimations. They're not going to be perfect because I don't actually have an equation. If you had the actual equation for that line of best fit, then you could definitely get an exact value for these.